So far, we've worked with some simple higher order functions like map and filter. We've also seen how we can describe our own higher order functions and how we can use lambdas to help us in that process. Now, higher order functions exist to abstract away common patterns. That's what one of the key ideas behind functional programming is, abstracting away patterns that you see repeatedly, and that's what map does. It abstracts away the pattern of transforming a list of one type to possibly a list of another, or just altering values in a list. Filter is much the same in that it abstracts away the pattern of getting rid of elements of a list that don't meet a certain criteria. This is what we want. We want to make our code reusable. We don't have to write these things from scratch. In this video, we're just going to have a look at some more examples to get a bit more practice when working with higher order functions and defining our own. So, we've got 3 exercises here. We'll just go through them one by one and try and have a little think about the types of these functions as we go along. So the first one is define repeat apply, which applies a function to a given input a given number of times. So this is something that takes a function f, a value x, applies f to x n times, where all of those are supplied as input. So let's have a look at what this should look like. So we'll call it repeat apply, and we'll give it the type. We know that we need to apply the function a given number of times, and the most sensible type to use for this would be int. You could use other types, but this seems simple enough and does the job. Then we need an input, and I want to make this function as generic as possible, so I'm going to give it the type a, because I don't know what the type will be, but I want this to be able to be applied to any number of types. And then we need to think about the function. Now, it's certainly going to have to take something of type a as input. You might be tempted to say that this should be a function from type a to b, much in the same way that map is, to aid us in a more polymorphic style to give us more types to work with and a more generic function. However, this function has to be applied to the same type over and over again, so we can't actually have a function from a to b, because after the first application we would then have a value of type b, and we would not be able to apply the function to that again because it takes values of type a. So what we need to have here is a function whose domain is the same as its codomain. That is to say, where its input type is the same as its output type, so that we can keep applying the function over and over again. And then we just want to return the result of this repeated application, so that should just be type a. So far, so good. Now, let's think about our base case. We're going to have to recurse through this because we don't know how many times we're going to have to apply this function, so we need to figure out what the base case would be. My best guess would be to say that when the integer that is the counter, the number of times it needs to be applied, reaches 0. That's when we should terminate. So I'm going to say the base case is where we have a 0, an a, no, let's call that x, and an f. And in this case, we should just return x. That's the value that we've got so far. If we're asked to not apply the function by supplying a value of 0, we should just return the value that we started with. Then we need to figure out how to do the recursive case, where we have an n here, an x here, and an f here. Now what I would suggest is that we update the value of x using f, and we subtract 1 from n, so that we're decrementing the counter and moving towards our base case. So this would be n minus 1, so we take off one of the applications, f of x, and f. Now f of x is going to be the new value of x that's passed to the next application. So if you think of this as a case where we get a value of 1 here, we would apply f of x once, we would reduce this to 0, and then we would return the value x. But now that we have our definition, we can test this out. So we can say repeat, apply, and I'm going to give it something simple, so I'm going to say 3, I'm going to give it a value of 0 to start with, and I'm going to say plus 1. This should just count the number of times that it's applied, and of course we get 3 out. Now you could certainly do something else here. You could use multiplication, you could use any number of things. One way you could think about this is moving towards a fixed point. As a fixed point of something that's f of x is equal to f of x, where your guess doesn't get any better, you keep staying at the same point no matter how many times you apply the function. You could think of it along those terms. The next question says define compose, which takes 2 functions and evaluates their composition. Now the composition of a function is to apply one after the other. So you give the first one some input, and then you apply the second one to the output of that function. So if you have a function from a to b and a function from b to c, the composition would then be function from a to c. So they need to agree in the middle there. the codomain of the first needs to be the domain of the second. So the output of the first needs to be the same type as the input of the second. This one's a little bit trickier though, because we're asked to take two functions and define their composition. So in higher order functions thus far, we haven't actually seen ones that take multiple functions. However, that's very simple to do. It's very straightforward. So I'm going to say, also, I think this is in the wording, this evaluate means we should apply it to a value. You could define composition which just returns the function. That would be strict composition. However, this is just going to evaluate them. It's just going to apply them to a value. So I'm going to say we should take a type A, something generic. And then we need to take a function, so that would go in the brackets. And I'm going to say we should take something from A to B. Because here we're not constrained in the way that we were above. We don't have to restrict the input type to be the same as the output type. And in fact, we wouldn't want to. We'd want to make it a bit more generic. They can, of course, be the same thing. A and B can be the same type here. But we want to say they don't have to be. And then the next step would be to take a function from B to C. And then we would return, hopefully you can infer this, but this should be a function to C in the end, because we're applying a function from A to B and then a function from B to C. So we should hopefully get something of type C out in the end. And then we say compose, if we could type, we could anyway. And let's say we get a value of x, a function f, and a function g. Now this one's actually going to be quite straightforward. We're going to say g of f of x. And this is quite similar to the way you would write composition in high school maths. You would just say g after x. Sometimes you use a little circle. In Haskell, there is actually the built-in composition operator, which is a dot. You can use that for function composition if you wish. I try not to, just so that you can see the nuts and bolts of everything as it's being applied. And it might be best for the purposes of this class just to stick with composition written in this way rather than using the operator. However, that's up to yourself. But anyway, that's defined composition there. So if we go on to the next one, we're asked to define higher map, which uses compose to apply two transformations to a list. So not only are we going to take in two functions as input this time, we're actually going to use a higher order function in the definition of our higher order function. So we're going up levels and levels here. So we have higher map. So this says to apply two transformations to a list. Now map, if I remember rightly, has type A to B. So I think I would, A to B, a list of A's to B. So we'll put the functions first this time. We'll say A to B, and then we can use B to C. Then we'll take a list of A's and return, hopefully, a list of C's. So we get an F and a G, and then we need to think about our cases. Now we're working with lists again. We're not going to use, we could use map, we'll maybe do that after this one, but we're going to define this as if we didn't know how map worked. And it's going to be quite straightforward. It's going to be defined much in the same way that map is. So we need to think about our base case because we're going to recurse through the list. And that's going to be the empty list, as it usually is when we're working with lists. And then we need to decide on what's going to happen in the case where we have x cons x's. So we're asked to use compose. We could do this another way, just using the functions themselves without using compose, but we're asked to for the purposes of this question. So we need to figure out how to get a value of c, and that seems like the way to do it. So we'll have compose, and we'll have, that takes the x first, so x, and then we'll have f of g. And then we'll concatenate that onto the recursive call of higher map f, g, x's. So now we can test this out and see if it works. So we can have higher map, and I'm going to say, let's start with something simple. We'll say something like times 5. That's simple enough, and then we'll say show, just so that we can see that we're translating types. Now the show function, you've seen this as part of the show type class, but that will just turn something to a string. That's how we represent it on the terminal. So for example, if you applied show to the number 1, it would just put quotes around it and then show 1 in quotes that way. But that's just so you can see that we can go from int to int and then from int to string, so we can change these types. So let's say we want to do this on 1 to 5. And there you go. So we apply the multiplication first, and that's where we get the larger numbers, and then we turn them into strings. In fact, if you wanted to, you could wrap type colon T around this and see what type it is. I also said that we could define this another way using map, so let's see how we would do that. So we had f, g, x's. Because map automates away the recursion, we don't actually need to worry about doing that ourselves, so I don't need x colon x's. What I do need to worry about though is I'm going to use compose here. So I could do this question in two ways. but I would need a lambda function here. I can't get away with partial application because the first argument is the one that's currently missing. If this was compose x fg, or fg then x, then I might be able to partially apply it. But I'm going to use a lambda, so I'm going to say I get an x as input, and then I go to compose x fg. And then I just apply x's. So if I've done that right, I should be able to load this in. Oh, that's because it's got the same name. Give that prime. And that's fine now. So let's say we do the same thing again, but with map prime. And there you go. So you can see that using these higher order functions, even when you're defining higher order versions of them, you can still automate quite a bit of the work away. So I don't have to repeat this recursion scheme because map does that for me. That's the power of these higher order functions. Even if I want to make a higher order version of them, I can still employ them to do that. But that's everything for today. I hope you found this useful. I really just want you to get comfortable with the idea of defining your own higher order functions, using them. They're really not too complicated. They're nothing too much to worry about. But of course, if you do have any questions about this, please do feel free to get in touch. Thanks.